Okay, so this first lecture is basically on simplifying your network using skeletonization techniques. So what is skeletonization? So this is about removing extraneous pipes to simplify your system. And this applies to WaterCAD and WaterGems as well as Hammer, but it's often used in Hammer because usually you want to focus just on the trunk main or the main pipes that will tend to have the biggest transient impact. So there's two different skeletonization approaches. One is to actually destructively delete pipes and make some type of decision as to what to represent at that point where you deleted it, maybe a demand or a boundary condition like a reservoir. And the other technique would be to replace that pipe or multiple pipes with one hydraulically equivalent pipe. So basically simplifying multiple pipes into one hydraulically equivalent pipe. So if you delete pipes, then that can actually change system capacity and make things that are make it such that it may not necessarily be hydraulically equivalent. Whereas if you use something like our Skelebrator tool, which is included in Hammer, that can actually simplify the model while maintaining hydraulic equivalency. So a note on Model Builder: normally if you're using Model Builder to bring in data to create your hydraulic model, oftentimes that data source may contain too much information, an all pipe model that has a lot of information that you may not necessarily need to include. So oftentimes, we talked yesterday about Model Builder and the process of importing data to start your network. So usually the logical next step is to then, if appropriate, simplify the network with something like Skelebrator or some manual technique. So skeletonization and transients. Systems often are skeletonized for transients, as I said, because usually you don't need to analyze the entire city model. It would just take too long for you to do that. It would take a lot of time to sort of clean up the little things that maybe you could get by with in WaterCAD or WaterGems, but Hammer, as we talked about before, is I guess we'll say picky, but it is more sensitive to modeling artifacts and little things that, like I said, in WaterCAD or WaterGems, it may have been fine. You may have gotten the right pressures or the results that you needed for that type of analysis. But in Hammer, when we're dealing with how waves are reflecting and interacting, you really need to make sure that the model is physically accurate. And therefore, oftentimes you can skeletonize it down to just the main areas that you will actually have the biggest impact, and that helps a lot as far as the time taken to clean things up and the time taken to actually compute the model, and also the file size. So what about that loss of detail? I mean, if you're simplifying the model, is there going to be a cost as far as accuracy? Are you going to end up with something that's less accurate? So what type of detail do you need to include to make sure that it's accurate? Well, you have to consider wherever there's mass or momentum that could change, those things need to be included. So things like branches on long pipelines, large diameter dead ends, where things could, where you will likely have a significant transient that will still propagate to there and still be, not dissipated at that point. And may reflect and possibly interact with other waves or areas that are closer to the area that you're analyzing. Those things really should be included versus, imagine a full city model. If you're modeling a pump shutdown way in the south corner, all the way in the north side where everything is all branched out or looped, most likely the transient, by the time it gets there, it has branched off and gone through so many different paths and so many different changes in direction that more than likely the transient energy has dissipated by then and dampened out. Also, some things that you will want to make sure you don't simplify out or remove in the process of skeletonizing the model, any significant elevations. So if you have a local high point, a knee like we saw in the workshop model, those really are important to include because of the fact that vapor pockets could be a concern. So any any little local high points where you're most at risk of experiencing negative pressure or possibly sub-vapor pressure, you want to make sure you don't remove those in the process of skeletonizing the model. So if you did, then you could be missing out on a potentially significant vapor pocket that may be forming and then collapsing, as we saw before. So if you were to imagine a large model that was skeletonized down to a much smaller version, here are the benefits. So you're just working with it in general. It's very, it's much faster. Opening, saving, file size is smaller. It's easier to do things. It's easier to navigate and find what you're looking for. You don't have to zoom in and sort through a giant list of elements. If you do it right, then the results can still be quite accurate as far as the main intent that you are trying to use the program for. So you have to think about do you really need to have that level of accuracy, and do you really need to know what's happening way out in the system, or is it more appropriate to just focus in on that main pipeline and maybe a few other nearby areas that will experience the highest maximum pressure or the lowest minimum pressure? So let's take a look at an example here. So this is a case that we saw yesterday, or maybe the day before. So at the top you have, this might be a GIS that was imported, and you have lots of extra detail. In the middle, this is probably how it will come in with Model Builder. So you have lots of extra pipes. And then after you run the Skelebrator tool and you simplify it down, the bottom is what you'll probably end up with. So only the significant points. And maybe this junction right here might represent a high point. So it's something you'll want to look at first, instead of just importing the entire model and then running Skelebrator on the entire model without doing any preparation. That's where you could accidentally remove some of those high points or significant areas. So it does take a little bit of preparation time, kind of understanding the system after it's been imported and cleaned up before you actually go and fully skeletonize it. So the Skelebrator tool, as I said, is included in Hammer. It doesn't need an extra license. It's a module that's within Hammer. It used to be an extra module within WaterCAD and WaterGems. In Hammer, it's included, so it's no extra cost to run it. So there's many different types of operations that could be run in Skelebrator. So these are the different options that you get, and we'll talk a little bit about each. The little icon there that says HE, that means that method will ensure that the end result is hydraulically equivalent to the full pipe version. So, and by that what we mean is, basically the same head versus flow relationship. So for the same flow through that stretch of pipes, you will get the same head loss. So that might be a matter of, if it's two different pipe sizes and you end up with one pipe at the end, it's going to use a diameter that's, if you elect to change the diameter, it will end up with a diameter somewhere in the middle that will be hydraulically equivalent. As far as demand allocation, so Skelebrator, if it's using a method that has hydraulic equivalency, it will ensure that any demands that are on nodes that were removed as part of the skeletonization process will be preserved in some way, so assigned to the next closest node, for example, that was still present in the model. Now, one note here on water quality effects. So hydraulic equivalency doesn't necessarily apply to water quality, so there could be some effects as far as water age and tracing of constituents, but usually you'll be dealing with a more complete, full model if you're doing water quality. So we're really talking about Hammer and transients here. So some general rules for skeletonizing. Again, and this is the rules for Skelebrator. It won't remove nodes that are significant, like pumps, control valves, tanks. It'll remove junctions if it needs to, but other things like pumps, controls, tanks, those will always be kept, and it won't leave things like that at a dead end. So you won't end up with a pump at a dead end, because a pump needs to have a suction and a discharge pipe. Also, you can designate protected elements. So if you don't want to skeletonize a certain area of the model, or you want to focus skeletonizing only a certain section, you can set up a selection set and use that. And that's where things like those local high points or knees, that's where you'll have to identify those ahead of time. So perhaps create a selection set of those junctions, those pipes next to those high points, things like that, where you want to end up with a skeletonized model that still has those included. So there's also a preview option, so you don't just hit a button and then it's done and you can't go back. There's a preview option where you can see exactly what it's about to do before you click the compute button in Skelebrator. Although once you actually commit that change, if you compute and commit the changes that it's suggesting, there's no undo, so you can't go back to the way it was before unless you, of course, save a copy of the model before skeletonizing, which is certainly a recommendation. So as far as elements that can be protected, you can protect both pipes and nodes, which means that they will not be removed during the skeletonization process. And that's regardless of what type of Skelebrator run you are using. And also, those protected nodes, it won't just leave them off in space, not connected to anything. It'll ensure that there's something connected to them as well, and they're not orphaned. So again, 2 steps. First, you do a preview. Well, actually, it's a bit more than that. So first, you define what type of operation you're going to run. So there's different Skelebrator types. You set up the different settings and the conditions, like what type of change you want it to make, whether it's diameter or roughness, what protected elements you want. And then you can choose to either apply those changes manually. It'll go through pipe by pipe. Do you want to do this? Yes or no. Do you want to do this? Yes or no. Or an automatic where it just applies everything at once. And then, as I said, there's a preview that's usually a good idea to run beforehand. And the preview basically will color code in the model plan view which elements will be removed. So here's one of the Skelebrator methods, smart pipe removal. So you have your conditions where you can specify the attribute that you're going to apply it to. So maybe you only want to apply the skeletonization to small diameters, and you want to keep all the keep the large diameters the way they are. So you can specify different conditions for skeletonization. And then you have your settings where you can kind of move the slider, actually literally, to make some tweaks as far as just how aggressive will it be at skeletonizing things. And you can run this in passes. You can run one pass and then check the results, and then run it again. It will even further skeletonize. But generally, this smart pipe removal option is usually used if the other methods are not being very effective. So this is something that you kind of have to play with. It's different for each system because there's looped systems, there's branch systems. Every system is a little different. So usually you want to experiment with the other methods first before you end up choosing the smart pipe removal. So here's an example of what you might end up with. It doesn't necessarily ensure that it's going to be hydraulically equivalent at the end. So that's why you usually want to leave this option till later, because you could end up with a gap like that. If it removes that pipe, in the dashed line represents you're left with a gap, and that could leave you with a system that's definitely not hydraulically equivalent. So you definitely be careful and do your preview if you do choose to do the smart pipe removal. Branch collapsing is another type of Skelebrator run. So that removes pipes and end nodes at the end of a branch. So if it's a branched system, this might be a little bit more effective. And the settings include just how many levels of collapsing those branches do you want it to run in one Skelebrator pass, so to speak. And this has an option as far as what to do with demands. So you can choose how it will treat demands on nodes. Should it move the load or do something different? And then you also have the conditions as you had in the other methods. So here's an example of a branch collapse. So at the top you have this is, what it starts off with. So the little junction there marked with the number 6 is removed if you choose one level of branch collapse, and you can see in the middle that at node 6 is removed. And if there was a demand on that, it probably would have been moved to the one marked as 10. And at the very bottom, you get a very simplified version where maybe it's collapsed 4 levels, and it brought the 9, 7, and 10 from the middle diagram there and combined them all into that 28. So I think the 28 that's referring to the demand in GPM. And you can see how it combined that together there. Series pipe merging. So this is combining pipes in series, as the name would indicate. And this is hydraulically equivalent here. So when it's combining pipes in series, it's the single pipe that you end up with is hydraulically equivalent to the pipes that you started with. So like I said before, if you have like a change in diameter or roughness or something like that, the single pipe that you end up with might have a diameter somewhere in between or a different roughness such that the relationship between flow and head loss is the same. So here's the settings for series pipe merging. I won't go into too much detail on that. As far as naming equivalent pipes, so the new equivalent pipe you create will have a new pipe number, and it will be automatically given the number of the next pipe to be added. So it might be helpful to set up your element labeling so that the new equivalent pipes will have their own labels. So you can change the pipe prefix, for example, from P to a EP for equivalent pipe, or maybe add a suffix like E for equivalent. So that way you can tell which pipes are equivalent pipes versus something that was still original when you're looking through the model. So to change the pipe labels, that's under a Tools Options, and then there's a Labeling tab. So there's an option in there where you can basically choose your labeling convention for new elements. Okay, parallel pipe merging is another Skelebrator option. So that's a different type of run. That one's also hydraulically equivalent. That's the HE. So this, as the name would indicate, it's merging pipes that are parallel. And let me skip ahead to an example here. So this is obviously a very simple case where you have two pipes that are directly in parallel, and then you end up with one equivalent parallel pipe that again has the same hydraulic capacity as the original two. Inline isolation valve replacement is another Skelebrator option. This one is a little bit different. So this is about taking cases where maybe you imported a model through Model Builder and you mapped say you have a layer in your GIS that has basically isolation valves. And maybe you bring those in as like a TCV element or a GPV element, which will snap pipes to the ends. The pipes will snap to those node elements. But if those really represent isolation valves, that can add a lot of extra pipes to your model. So you have, like in the example at the bottom here, you have 3 pipes because there has to be a pipe on either end. We have an isolation valve element that does not snap to pipes. So the isolation valve, it's a node, it's a point element, but it's associated with the pipe. So you don't connect the pipe directly to it. There's a property in the isolation valve where you choose the associated pipe, and it draws a little dashed line to the pipe. So this inline isolation valve replacement option in Skelebrator will convert cases like this where you have lots of extraneous valves that really aren't doing anything under normal operations and just creating lots of extra pipes. It will convert those to isolation valves. So you end up, in this example case, going from 3 pipes to 1 pipe. And you can imagine in Hammer how important that could be because of the fact that the wave needs to travel from one end of the pipe to the other in even increments of the time step. So you can get a notification that says there has been an excessive adjustment to the wave speed or length, and that's because of short pipes, like cases like this where you have a pipe included here and this one here that maybe could be quite short. Whereas if you convert those to isolation valves, which means they're probably just fully open, during your initial conditions, then you just have one pipe, and then you don't have to worry about Hammer artificially adjusting your pipe lengths or your wave speed. So here's another example of the power of Skelebrator. So starting from the left side here, this is an example of an original model. So you run a branch collapse that brings this node down to here. Then maybe you do a series pipe removal, and that combines these two pipes that are in series into one, and then back up to the top right. So maybe you run a series pipe removal again, and that looks at this pipe in series and turns those into one. And then you run a parallel removal, and that takes these two parallel pipes and makes one equivalent parallel pipe. And then maybe you do a further series pipe removal, and then you end up with just two pipes with probably a demand in the middle. So you can see the process that you might follow. This is a simplified case, but this can be applied to full pipe models. So skeletonization as it applies to transients. So again, some rules for system simplification. You always want to include your boundary conditions, which Skelebrator will not remove, but those are important to include even if you're maybe manually simplifying your model. So things like tanks, pumps, any type of surge control valves that would impact a transient event. And then, as I said before, it's very important to include significant elevation extremes so that you don't miss out on possible vapor pocket formation. Some second order effects. So, in some cases there might be key loops that may dissipate transient energy, and if you skelebrate those out, then maybe your results for transient simulation are conservative, but in some cases, if you have a very key loop that helps in dissipating that energy, then you may be over-designing the system. So you kind of have to have a good understanding of the network and the topology. Also, large diameter branches or loops may be significant. So even if these pipes are relatively far out in the system, if they have a large diameter, then there's a potential that the transient waves may travel down those pipes and reflect back and still be significant by the time they reach back to the other areas of interest. So a practical example of a procedure here. So you're starting with an all pipe model that maybe you brought in through Model Builder. You run Skelebrator, skeletonize it. You analyze transients with Hammer. So an example of 5 levels of Skelebrator, maybe you start with a 261 pipe model, then you get it down to 143, 107, 16, and you could actually get it down to 3 pipes. So here's the case in question here. So we start with the model on the left here that has 261 pipes, and then we end up, after one Skelebrator run, a model that has 107 pipes and has the same shape, but you can see like over here these two pipes were in series, and now they're one pipe, and you can kind of see how it's simplified things. So further, if you get it down to 16 pipes, this is what it'll look like. You have your main pipes are still included, and you can kind of compare that to the original. So it's got the same original shape, the same boundary conditions, but you've simplified it down. Now here's the effect on the system head curve. So looking at a system head curve is a fairly good way to assess the sort of system conditions for a range of flows. So you can see that the green line here is the 3 pipe model, and that is a bit more of a significant change to the system head characteristics versus the other one. So maybe the 16 or the 43 pipe version of the model may be appropriate. So this is the type of analysis you could do. If you have a pump, you could run a system head curve as you start skeletonizing the model to see if it reaches a point where there's a significant impact on the overall system head curve. So Hammer analysis here. So this is a little example that we'll see some screenshots of. This is a pump trip, emergency pump shutdown. Takes 3 seconds to run down. It's using the unsteady friction method, transient friction method. Pumps running at 3,500 RPM. Pipe wave speeds are about 1,000 meters per second, and a duration of 30 seconds. So this is the profile you can see here at the top of the 3-pipe version, and at the bottom is the all-pipe version. So you can see there's some circled knee points. So these are potential local high points that could be significant, some of which were removed in the 3-pipe version, especially the one way over on the left. You can see that one is up at almost 480 meters. It would have been up here, and that's, because we only have 3 pipes, it kind of removed that. So if we take a look here, here's the 43-pipe version versus the all-pipe version, and the local high points were removed. This just to make that point about how important they are. You can compare the bottom to the top and see how, even the 43-pipe version, it's got that main knee way over on the left, but it did miss a couple of other local high points. And there's the 16-pipe version, missed out on quite a few there. So if you were to run a transient simulation, some observations, basically as long as the hydraulically equivalent pipes are used, the overall transient head envelope doesn't dramatically change until you get so low that you miss out on those high points. So reducing the number of pipes tends to increase the severity of the maximum and minimum transient heads because it eliminates some of those pulse fragments and attenuation mechanisms, but not if you're removing significant high points that may have otherwise caused vapor pockets to form and then collapse.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.